Today on Macaulay Math, we're looking at geometric sequences and series. Intro. Okay, good day. I'm Professor Macaulay. This is Math 150, Pre-Calculus, Lesson 37 on geometric sequences and series. Our goals for today: we're going to find the explicit and recursive equation for a geometric sequence. We're going to find the sum of a finite geometric series, and we're going to find the sum of an infinite geometric series. In the last lesson, the concept of sequences and series was introduced. Additionally, arithmetic sequences and series, a specific type of sequence and series, where each term has a common difference, was discussed. This lesson covers a second specific type of sequence and series called the geometric sequence. Whereas the arithmetic sequence has a common difference between successive terms, the geometric sequence has a common ratio between successive terms. Let's get started. Okay, let's start with a definition. A geometric sequence. A geometric sequence is a sequence where each successive term is multiplied by a common ratio. And as an example, 1, 3, 9, 27, 81. This sequence has a common ratio of 3. 81 divided by 27 is 3. 27 divided by 9 is 3. 9 divided by 3 is 3. And 3 divided by 1 is 3. That is our common ratio. The general form of a geometric sequence, where a sub 1 is the first term and r is the common ratio, is a sub n the nth term. And again, this is an explicit form of the formula for a geometric sequence. Y equals ab to the x. And we can find the sum of the terms in a finite geometric series by saying the sum of the first n terms is equal to the first term times the quantity 1 minus r to the n power all over 1 minus r. And some quick elementary examples: a finite geometric sequence, 1, 3, 9, 27, 81, 243. A finite geometric series, 1 plus 3 plus 9 plus 27 plus 81 plus 243. And this notation asks us to find the sum of the first 6 terms of a series. And adding up 6 terms of any sequence isn't too hard to do by hand, but you can see very quickly that these numbers are going to get big very fast. And so it's going to be very beneficial for us to use this formula right here. So S sub 6 will be the first term, which is 1, times 1 minus r, which in this case is 3, to the number of terms we're adding up, which would be 6, all over 1 minus r, which is 3. So that is a calculation that I don't want to do by hand. So we'll go over to Desmos. Since there's an operation in the numerator, we'll put a parenthesis around that. Then we'll go, we don't need to go 1 times, but I'll do it this time just so that you can see it's in there. And then 1 minus the common ratio 3, shift 6 to bring an exponent up. I'll put a 6 up there. I will close that parenthesis, then close the numerator, and then I've got 1 minus 3 at the bottom, and we get a sum of 364. 364. And that is the basics. But what happens if I take this series, I flip it around and start with 243 and then multiply by a common ratio that makes it smaller? So in this case, if I multiply 243 by 1/3, I get 81. 81 times 1/3 is 27. 27 times 1/3 is 9. 9 times 1/3 is 3. 3 times 1/3 is 1. 1 times 1/3 is 1/3. And 1/3 times 1/3 is 1/9. And we keep that going for forever. Well, it turns out that you can actually add up the sum of an infinite geometric series, provided that the absolute value of the common ratio was less than 1. I know that's wild, but you can see very quickly. Let's just put that sequence into Desmos. We'll go f of x is equal to, it was 243 times 1/3 raised to, and we need a parenthesis because we're going to go x minus 1 in the numerator. You can see really quickly that by the time I get to 15, I can't tell the difference in Desmos between the function and the x-axis. So these numbers get so small that we can't tell the difference between them and 0. They're almost 0. And when you add up a bunch of things that are almost 0, it becomes insignificant. So you can actually make that calculation. So I'm going to do it the same way. I'm going to go s is equal to the 243 over 1 minus 3, and we'll just put that calculation quickly into Desmos. And we get a final answer of 364.5. as our final sum, which is pretty crazy to me because this infinite sum is only 1/2 bigger than a sum that we did in the previous example that had only 6 terms in it. All right, next example. It says find the first 5 terms of a geometric sequence that has a first term of 5 and a common ratio of 2. Well, they tell us that this first term is a sub 1, and this is my common ratio. So I'm going to use that formula that we were given for the general form of a geometric sequence, and we'll say a sub n is equal to a sub 1 times r to the n minus 1. So in this case, a sub n is going to equal to 5, common ratio of 2 to the n minus 1. And that is the formula for the first 5 terms of a geometric sequence. They want us to find those first 5 terms, so that'll be a list. And we're going to use Desmos to calculate that and make a table. So we'll go back over to Desmos, and this time I'm going to put that formula in as a function. And again, the reason that I want to do that is because I'm going to use a table. So we'll go 5 times 2, and then it's raised to, and again, since I'm doing an operation in the exponent, I'm going to put parentheses around that. Close that up. We'll make a table, and we will change that y1 to f of x1. And the first term, the second term, third term, fourth term, fifth term, 5, 10, 20, 40, 80. And that is our list of the first 5 terms in that sequence. All right, next example. Find the first 5 terms of a geometric sequence with the following recursive definition. So here they're giving it to us recursively instead of explicitly. And they want the first 5 terms, but they give us the first one. So we will thank them for a little less work and put that 80 down there. And the second term, a sub 2. Well, if a sub 2 is equal to k plus 1, then k has to be 1. So we know that a sub 1 is 80, so we'll plug in 80, and then we will multiply by a half. That'll give us 40. Put that up in my list. Then a sub 3 will be equal to, so if k plus 1 is 3, then k is just 2. So I'll have a sub 2 times a half. And then we just calculated what a sub 2 was. It was 40. We'll go 40 times 1/2. That'll give me 20. And I see the pattern here. We're not going to waste a bunch of time going through all of these. If I can say that I'm going to multiply 20 by a half, that'll give me 10. I'll multiply 10 by a half. That will give me 5. And that is my solution. All right, next example, it says find this sum. So if I start plugging these values in, I'll go, my first term would be when n is equal to 1. Now when I plug in 1 into this expression, I get 1 minus 1 is 0. 3 to the 0 is 1. 1 times 4 would be 4. We'll do the one more plus here. My next term will have an n equal to 2. 2 minus 1 is 1. 3 to the first is 3. 3 times 4 would be 12. And I can see that the remainder of these terms would be multiplying each successive term by 3. So 12 times 3 would be 36, and we would get that on for 20 terms. Now, the sum equation for geometric series does not require you to know the last term. In fact, if I rewrite it, S sub n is equal to a sub 1 times 1 minus r to the n all over 1 minus r, all I need is the number of terms, the first term, and the common ratio. So that makes doing this sum much easier. All I need to do is go S sub 20 is equal to 4 times 1 minus 3 to the 20th power all over 1 minus 3. So it's going to be similar to the first equation, but again, notice, have to write in that first term right there. So back in Desmos, we will go parenthesis for the numerator, 4 times 1 minus 3 raised to the 20th, close that parenthesis, close the numerator, divided by 1 minus 3, which would be negative 2. And so clearly, this is an instance where we see that geometric series can grow quite fast. 3 to the 20th is a pretty big number. And so my final answer for this problem, I'm just going to write it in scientific notation. And again, we'll round to 3 places because it's crazy big. And so we'll say S sub 20 is equal to 6.974 times 10 to the 9th. So that's going to be a 6 with 9 places after it. That's a pretty big number. All right, next example. It says, write the following geometric series in summation notation. So I look at this. I have 2 and then a 6 and then 18 and then 54. I clearly know that this is my first term, a sub 1. If I do some divisions, 54 divided by 18 is 3, 18 divided by 6 is 3, 6 divided by 2 is 3. So I know that my common ratio R is, in fact, 3. So if I go to do my summation notation, I go summation equals I equals 1. What I don't know is how many terms. What term is that? Well, I can calculate that using that general form of the geometric sequence formula. And I already know what that is. It's going to be 2 times 3 to the I minus 1. I just need to figure out what term 1458 is in the sequence. So what I'll do is I'll say a sub n is equal to 2 times 3 to the n minus 1. And since this is the nth term, I don't know what n is, I'm just going to plug this number in there and solve for n. So we'll go 1458 equals 2 times 3 to the n minus 1. Now I know we haven't solved one of these for a while. We did a bunch of trig, but right before we did trig, we were solving exponential functions. So let's remember back. And the first thing I'm going to do is I'm going to divide by 2. 1458 divided by 2 is going to be 729. So I have 3 to the n minus 1. Now we could go through and just hammer out a multiplication. It wouldn't take us very long, but this is a pretty big number. The easiest way for us to figure this out is to use a logarithm. And so I'm going to take the ln of both sides. So we'll go ln of 729 equals the ln of 3 to the n minus 1. And what that's going to let me do is bring this exponent down. And so I will use log base a of x to the n is equal to n times log base a of x. And so I'll have the ln of 729 equals. Now I'm bringing the whole exponent down, so I'm going to put parentheses around that. And then we will divide by ln of 3 And that will give me the ln of 729 over the ln of 3 equals n minus 1. And here I'm just going to add 1 to both sides, so I'll have n equals the ln of 729 all over the ln of 3, all plus 1. And we'll just put that into Desmos. ln 729 divided by ln of 3. And then we need to add 1 to that. And so 7. So it turns out that there are actually 7 terms in this series. Put a 7 there. Put a box around it. And we are finished. Next, it says determine if the following. So if I look this, 15 divided by 30 is a half. 15 halves divided by 15 is a half. 15 fourths divided by 15 halves is a half. So this thing has a sum because the common ratio, the absolute value of the common ratio, which is the absolute value of a half, is less than 1. And so that sum is the first term, a sub 1, all over 1 minus the common ratio r. So we'll go s is equal to 30 over 1 minus a half. Now I could actually calculate that. I'll go 30 divided by a half. When I take how many halves are in 30, there are 60 halves in 30. Now when I look at this one, 1/4 times 2 is a half. A half times 2 is 1. 1 times 2 is 2. 2 is 4. This one does not have a sum. Because the common ratio r, which in this case is equal to 2, is greater than 1. So it is unbounded. It'll grow without bound and be infinite. All right, last example. It says, and I really like this last example because it is a quote-unquote real-world problem. If you think back to the kinds of questions we did back when we were doing exponential functions, we say, okay, you've got $10,000 and you put it in an account for 15 years at 3% interest. That's compounded monthly. What do you have at the end of the 15 years? Most of you are not going to be able to save your money like that. Most of you are going to take a little bit of money, put it into account, and save a little bit after a little bit after a little bit until you're ready to retire. So this is an example of that, and we're going to get to see how that money increases over time. So the example says a deposit of $125 is made into account at the beginning of each month that pays 3.5% interest compounded monthly for 5 years. This is called an annuity. Write a geometric series that models the situation. Well, that's pretty simple, but let's real quickly refresh our memory. Remember the equation A is equal to P times 1 plus R over N all to the NT. And basically, the geometric series that we're going to set up is going to be using this where we're calculating how much interest each deposit of $125 as it's in your account for 5 years. So they want us to write this series. And so think about it this way. You deposit $125, and at the end of the first month, it will have earned 0.0353% compounded monthly for 1 month. At the end of the first month, you deposit another $125, and you leave it in that account for a full month. This first $125 that you deposited has now been in the annuity for 2 months. So this $125 moves over here, and it still has the same calculation, but instead of being in the annuity for 1 month, it's been in there for 2 months. At the end of the second month, you deposit another $125, and then at the end of the third month, this first $125 it has now been in the annuity for 3 months. The second $125 has been in the annuity for 2 months. And then the third $125 has been in the annuity for a month. And that is going to last for 5 years. So after 5 years, this first $125 will have been in there for 5 years worth of months. Well, 5 times 12 is 60. So at the end of the 5 years, that first $125 will be in the account at 0.035% interest, compounded monthly for 60 months. And so this series represents each one of those $125 that you deposited into your account. All right. Now, it wants me to write the geometric series in summation notation. Okay, well, sum, and we'll use I equals 1. And we already know that there are 60 terms in here, so my upper bound will be 60. And this one's going to be a little bit different than the last one because it will be the sum of 125 times 1 plus 0.035 all over 12, not to the I minus 1, just to the I, because we start with the first term here. And note, I wrote N, but I meant I. So there is our series in summation notation. Find out how much the person will have saved and the value of the annuity at the end of 5 years. Well, finding out how much the person has saved, that's pretty easy. That is just going to be 125 times 60, because you will put 60 $125 payments into the account, and we can do that in Desmos real quick by going 125 times 60, and you will have saved $7,500. $7,500, that's our part A. But we want to find what the value of the annuity is. Okay, the value of the annuity will be that sum of a geometric series formula. S sub n is equal a sub 1 times 1 minus r to the n all over 1 minus r. And we have to choose that formula over the formula that we used in this last example, because this is the formula for an infinite series, whereas this is the formula for a finite series. All right, now we know that we are calculating the first 60 terms. Here's the hard part. We have to figure out what a sub 1 is and what r is. So if I go back up here to my first part of the question and I look at this geometric series, this whole expression right here, that is a sub 1. 1 times 1 plus 0.035 over 12 to the first. That is the whole first term. The second term is the first term times the common ratio 1 time. And the 125 is the same. All that I've done is I've multiplied this expression here by another 1 plus 0.035 over 12. So that portion of it becomes the common ratio. It is just the 1 plus 0.035 all over 12. This gets kind of mucky, but since I know that and I have Desmos, I can actually use Desmos to make it a little bit easier for me to type this stuff in. Because what I really need is 125 times plus 0.035 all over 12. That is my first term, times 1 minus, and then r is 1 plus 0.035 all over 12. And I need to raise that to the 60th power. And then I need to divide that whole thing by 1 plus 0.035 all over 12 again. Well, that's a lot to try and put into decimals. So if I say that A is just this first thing and R is just that thing, then I can come over here to decimals and say that my common ratio is just equal to 1 plus 0.035 divided by 12. That's my common ratio. And then I can say my first term, and I won't say A sub 1, we'll just call it A for now, is going to be 125 times that, times R. And what that allows me to do is to just use the formula. I can say that the sum of the first 60 terms is going to be, we'll put a parenthesis there for the numerator, the first term A times 1 minus R raised to the 60th, close the parenthesis for the parenthesis in the top, another closed parenthesis for the numerator, divided by 1 minus R. And here we get how much that they made at the end of that time. And it turns out that this S sub 60 is $8,207.13. And so over the course of 5 years, and so you have made an additional $700 over the course of the 5 years. Now that may not seem like a lot, and I understand that, but it is only over 5 years, and you're going to be working for 45 years. So just as a quick aside, we're actually done with the lesson, but I do want to show you a little something else. Let's just say, for the sake of argument, we changed it to, let's say, 5%. At 5%, you have now made $8,500, so there's 3. And let's say instead of doing just S, let's make it a function. Let's go f of x is equal to this expression here. And let's change, instead of 60, let's change this to x. So we're going to be plugging in months. And then let's make ourselves a table here. And we'll scroll down and we'll make this f of x1. And on this one, we'll go 125 times x1. And what the first column will do, will calculate how much you have in the annuity, and the second column will calculate how much that you've actually saved. So after 60 months, you saved $7,500, and the value of the account is $8,500. So if 60 months is 5 years, after 10 years would be 120, and then after 15 years would be 180. After 20 years, it would be 240. After 25 years, it would be 300. After 30 years, it would be 360. After 40 years, it would be 420 months. And then after 45 years, it would be 480 months. So after you've been saving until you retire $120 a month, you will have saved $60,000. But the value of the account will be $191,547. And hopefully, as you get older, you will be able to put more money into the account. So this number would go up a little bit, saving. And then since you've already got this nest egg, this number will go up faster as well. Clearly, saving $60,000 and having more than 3 times that by the time you retire is a good thing. So my suggestion to you is to start early. Well, folks, I hope you stayed around for that. But that's all I got for today. So, the Star Wars fun fact of the day. The sound of hovering battle tanks in Episode 1, The Phantom Menace, was achieved by running an electric razor around a salad bowl, then digitally lowering the pitch. I've got an electric razor. I've got a salad bowl. I should be able to make sounds for the next Star Wars movie. Well, that's all I got for today, folks. You have a great day. Goodbye.